Okay, so let's start. Two comments before I get to the real thing. I'll mention it later again. One is we do have a meeting also on Wednesday. So it's, even though it's Friday schedule, because there was no class here on Friday anyhow, I reserved the room. I know that some of you maybe want to be here, so it's going to be videotaped as usual, I just wanted to take the opportunity that there is time and do one more lecture. Yeah? Yeah. So that's the third comment. The second comment is that there is a survey out, and some % of you have done it. I would really appreciate if all of you do it. Please, it's going to take you 5 minutes. Even if you write comments, and many of you have written comments, in addition to just going through the survey, it's very helpful, can still impact the next few weeks, but definitely helpful for us, me and all the TAs to see. So we're going to give extra credit if at least 80% of you are doing it. So that's hopefully that's an encouragement. So please do it and ask your friend to do it. Third comment is that, and again, I'm going to go back to it later, I want to talk to all of you about the project. So please come to my office hours. If the office hours do not work for you, send me email and we'll set up other times. Many of you have already done it, but not all of you. So I will have office hours today. I will have office hours on Wednesday. By the end of next week, I hope that I've seen all of you. And these are the key comments. Questions? Yeah.
This is a question about the quiz, not about the project.
Okay.
But my understanding was that with many of the classifiers, if the weighted sum comes out to 0 exactly, it gets classified as a positive class, right?
So that's really an issue of definition. But I don't remember what we asked about it that is relevant in the quiz. The quiz dependent on this being exactly 0 or not?
Yeah, because I think in one of the questions, the decision boundary goes exactly through one of the points, and that point happens to be negative, in which case, if 0 gets classified as a positive class, that.
So this was the SVM problem?
Like, yeah, they realize there was a mistake. They will
Okay.
give credit to
So that
correctly, yeah, or you.
okay. That was an oversight. If that was the SVM question?
Yeah. Question 2.
Okay. We missed that, I guess. But yeah, it shouldn't matter. You can do whatever you want in principle with 0. So just an issue of definition. So we will not. It will not cost you. Other questions? Okay. So let's see. So we are still at AdaBoost. I want to finish it and start the next chapter today. So this is the algorithm. As we talked about last time, it's a really important algorithm, and the way it works is essentially looking at the data sets, focusing in each round on a subset of the data set, trying to learn a good classifier or an okay classifier for this, and keep on going. At the end, we are going to weigh all the classifiers that we learn into one final hypothesis. Now, the way we are focusing on a data set is not by just looking at a subset of the example, but rather by changing the distribution over the data set that we have. And that's really an important thing to understand. Why do we change the distribution? What is the impact of changing the distribution over the data set that we train on? What does it mean? You have a data set. You have 100 examples. What does it mean that I tell you that the distribution is such that there's a lot of weight on these 50 examples and little weight on these 50 examples? Yeah.
Basically means when you're calculating the cost, you get penalized more for getting those heavily weighted ones wrong than for getting ones low weighted wrong.
All right, so it's basically the error, which you called cost. So the definition of an error depends on, is a weighted sum of the mistakes. So if I have some examples that weigh more than others, and I want to reduce my error, I don't want to make errors on these examples that weigh a lot. And by changing the distribution, I kind of force my algorithm, therefore, to focus on different parts of the data set. So that's what boosting is doing. So just to run over the algorithm, I'm starting with uniform distribution. D1 of I is 1 over M. There are M examples. In each round, we are changing the distribution. So D, I'm defining here dt plus 1, the distribution at time t plus 1, as a function of the distribution at time t. And we're going to understand what it's doing there. So the way I'm changing the distribution is I'm changing the weight on each example, and I'm distinguishing between those examples on which I made mistakes previously and those examples on which I did not make mistakes previously. And once I'm done, I decided that I'm going to do this capital T rounds. I'm returning this final hypothesis, which is a linear sum of the hypotheses I've learned, weighted by this alpha. And alpha is a function of the error. Basically, what I want to do is I want to weigh heavily those hypotheses that had small error. That's it. And now to the details. So we talked about some of the details last time. So the first thing is we noted that alpha t is positive. And it's important for you to understand why it's positive. And if you look at this expression, again, by now, hopefully all of you know how to read a little bit of math. So you should convince yourself that alpha t is positive, and the reason is the assumption that we're making. The assumption is that for all t, which means in every round, we are able to learn a hypothesis that has epsilon error less than a half. And because epsilon is less than a half, 1 minus epsilon is greater than a half, and the ratio between 1 minus epsilon and epsilon is greater than 1, which makes alpha positive. Because alpha is positive, e to the alpha is greater than 1, which is just written there. Because e to the alpha is greater than 1, you should convince yourself that when I'm multiplying the previous distribution on example I by this, I'm increasing its weight. When I'm multiplying it by e to the minus alpha t, I'm increasing the weight, which means that if I made a mistake, second line here, okay. If I made a mistake, I'm increasing the weight of the example. If I got it right, I'm decreasing the weight of the example. That's it. So that's what boosting is doing. Now, and at every point in time, I'm normalizing because I want this to be a distribution. So I'm dividing by a constant z of t so that the sum over all the data points is going to be 1. I want it to be a distribution. Yeah?
What's the point of taking the logarithm there and then exponentiating it there?
Okay, good question. What's the point? So you say, who cares about alpha t? I just care about e to the alpha t? That's what you're saying. Okay. Look carefully at the slide. The answer is on the slide. Good question, though. Why did I care about alpha t and not only e to the alpha t? Yeah?
Final hypothesis.
Final hypothesis. Here I need alpha t. Okay, so during the algorithm, you're right, I don't need to do it. I can just keep it as 1 minus epsilon divided by epsilon square root. But at the end, I need alpha t. So therefore, I define it this way. Okay, so that's alpha t. And the other thing is zt, which I said you don't really need to care about because it's just a normalization factor. But you have to understand what is a normalization factor. So a lot of the things here are rather simple but insightful. So understanding the epsilon, it's the error, the alpha, the z are important because it will allow you to understand what's happening. So what is really z? Z is a normalization factor, which means it's the sum of the weight of all the examples. Okay, this I said this. Basically what I need is I need to make sure that the sum of all the data points, sum of dt of I over all I divided by zt is 1. That's what I mean when I say normalization factor, right? Which means that zt is just the sum over all I of this expression. Now, if you divide everything by zt, you'll get 1. Both sides, you'll get 1 on the right, on the left side. So that's our goal, and that, again, that's important. So we have an algorithm. Last time we played with this example, which hopefully was insightful. Go over the example. Make sure that you know how to compute epsilon. You know how to compute alpha. Convince yourself that you understand why looking at 3 mistakes here gave me epsilon of 0.3, and looking at 3 mistakes here gave me a smaller epsilon, and so on. And that's the hypothesis. I finished with this comment, which is an interesting comment. In principle, I did not have to finish after 3 examples. I could have run it more. Now, you know, because I stopped after 3 and showed you what's happening, that on these 10 examples, I make no more mistakes. But in principle, there will be other data sets on which just using 3 hypotheses will still make mistakes. So in principle, adding more and more weak hypotheses should help, and it does help. So AdaBoost in general is an algorithm that is hard to get to overfit. You can add hundreds or thousands before it overfits. Okay, so the next few slides are analysis, and I don't want to go into the analysis in details. I do want to point out a few things. Now it's only 3 slides. It will be useful for you to try to understand it. All the information is on the slides. I do want to point a few things. So what is the theorem? What do we know about AdaBoost? We know that if we run AdaBoost, and we have this assumption, somehow this green doesn't show well. Hopefully you can read this. What's written here? You can read it? No. Okay, so it says a half minus gamma t. What does that mean? It means that epsilon is a little bit less than a half. That's the assumption that we're making, that we can always learn with epsilon that is less than a half, better than chance. That's an important assumption. Now, someone came and asked a good question at the end of last time, and the good question was, how can you make this assumption? What happens if you have the data and you cannot learn with error less than a half? And this could happen. In real life, this could happen. But the assumption of AdaBoost, under which we're proving all the properties of it, is you can always do this. You can always learn with error less than a half. In practice, maybe sometimes you will not be able to do it. Nevertheless, it so happens that AdaBoost is very robust, even if in some cases, in some of the rounds, you did not manage to find a good weak learner. But anyhow, let's see what it says. So under this assumption, we are saying that the training error is less than this. What's written here is e to the minus 2 sum of all the lambda t's squared. So without proving it, what I want to understand is, or you to think about, is 2 things. One, why is the theorem stated in terms of minimizing training error? Is that what we want? Is the question clear? You could have complained, why are you stating a theorem this way? So let's start with the second part of the question. Is that what we want? Yes?
I guess you would prefer to talk about generalization errors?
Right. I mean, who cares about training error, really? I want you to guarantee to me that AdaBoost is going to have small generalization error. So why do I talk about training error, or why is it okay for me to talk about training error? Yeah?
You said it's hard for it to fit the data too well, or like it's hard for it to...
I said it's hard to overfit. Yeah. But that's just, you know, something that I said. It's not in the theorem, right? So you don't have to believe it. But the theorem, why does it make sense for someone to prove a theorem on training error and say, that's fine. That's really what you want. Yeah? Daniel?
You're assuming that the training data comes from the same distribution as the general data. It doesn't, but obviously can't vary.
Right, so learning theory, right? In the last few weeks, we showed that under reasonable assumptions, because we are actually learning a linear classifier in terms of the weak learners, if you have good training error, you're going to have good generalization. All right, so it's okay to prove statement on the training error. We proved that the gap between the training error and the true error is going to go down as a function of the number of examples we see and so on. So it's fine. If you know that the training error is going to be small, you know that you're going to generalize better. So that's one thing. Now let's read carefully. What does this say? I'm writing it here in two ways. One of them is sum over all t, gamma t squared, e to the minus this. And here I'm writing it in a simpler way. Because t is finite, I can just say, you know, let's choose a gamma that is less than all the gamma t's, still positive. And then I can say that the training error is then e to the minus 2 gamma squared times capital T. Capital T is the number of rounds. So what does this say? Can you say this in English? What is the statement? Again, this is something that you should get out of this class, which is the ability to read these statements and understand what they mean and whether they're good for you or bad for you when you want to use algorithms. So what does this say? Anyone? Back in the balcony, yeah?
So your gamma t is basically like the deviation from 1/2. And so you choose the smallest deviation from 1/2, so the one with the greatest error, and then you use that as a bounding on the estimation of training error. So you've substituted, you've chosen the smallest deviation from 1/2, the hypothesis with the greatest error, and then you use that as your gamma.
Right. And I promise you that I can always find epsilon, let's say 0.49, which means gamma is going to be at least 0.1, 0.01, right? So what does it say? If gamma is at least 0.1, what does it say about this training error? Gamma is a small number, positive number. So how does this behave? What does this mean?
Negative sign, is that...
It's negative. E to the negative, yeah, sorry about the color here. E to the, I thought it's going to be clear, but e to the negative 2 gamma squared times capital T.
That's the biggest error you can get, right? And the smaller the gamma...
Gamma is fixed, 0.01. Even smaller.
You multiply by 2, and then the negative of that is going to be...
But what could change here? As a function of capital T, what's going to happen? It's going to get smaller. As a function of capital T, the training error is going to get as small as you want, right? So this will go e to the minus something is going to go to 0, right?
The number of rounds?
T is the number of rounds, the number of weak learners that I'm going to use. So as I increase T, the training error could be as small as you want. Right? So that's basically the important thing here. So what AdaBoost guarantees to you is that you can add more and more weak learners, and your training error is going to go to 0. This is what it says, right? So you should convince yourself that you get this. Okay.
Always be able to go to 0, like no matter how messy, terrible that they are.
Okay, there is an assumption. What is the assumption? Gamma is positive, as you said. What does it mean that gamma is positive? It means that epsilon is less than a half. It means that every round, I can get a weak learner. Does this make sense? What does it mean that every round I can get a weak learner? Yeah? It's better than chance, but it's a strong assumption because whatever the distribution that you put on your M examples, let's assume this example is very, very difficult. At some point, the distribution is going to change and put all its weight on this example, right? Because if I make mistakes on it repeatedly, the weight of this example is going to grow. The weight of the other examples on which I got it right is going to go down. So at some point, perhaps all the weight is going to be on this hard example, and I will have to get it right because I need epsilon less than a half. Yes?
What would happen if you just pick any random hyperplane and you just guess the sign of it, say it's heading in the 1, 1 direction, and it turned out to increase the error, so you flip the sign. So it seems to me as if it's not that hard to come up with something that always yields. I mean, once you evaluate it on the training data, if it's not good, you just flip the sign and keep going.
Yes. And I'm going to change the weights and choose, again, a random hyperplane. A random hyperplane is going to make a mistake. So if you change it, now remember it has to be bounded away from a half. Right? So every time you'll have to do this trick. If you do it many times and you have hyperplanes that did better than a chance, actually it's going to be a good hypothesis. Right? What you did is something smart. For every distribution, it's not a random hyperplane, right? You actually had to do it in such a way that the weighted error is less than half. If you manage to do this for every distribution I give you, you did something clever. That's what it says, right? You can reduce the error completely. But the important thing is that actually it is a strong assumption because of the for all distributions. Okay? It's not just for uniform distribution over the data. And in fact, in practice, it's impossible to do. Right? It's very hard to do and will hardly happen. Nevertheless, what people found out is that it's actually quite robust in practice because for some of the T's, maybe you will not achieve this, but overall, you will, and the average is going to be quite good. Yes?
So would this be kind of inefficient in practice because you could have to remember many, many, many hypotheses and then calculate the weights over all of them? Like it would take
Yeah, think about each hypothesis as a feature. Right? So in the example that I gave here, what is a hypothesis? It's basically a feature, right? A hypothesis here was a vertical or a horizontal line. Yes, you'll have to learn a lot. So space-wise, maybe you'll have a few thousands of these. Not a big deal. Okay, so the rest of these 3 slides are analysis. I don't want to go into the analysis, but I do want you to look at it for 1, because it's very insightful, 2, because it forces you to think about what does error mean. So example, what is here? Training error is what? It's 1 over m, average over the example, sum over all I of 1 if I made a mistake, 0 otherwise. That's the definition of training error, right? I hope you agree with that. Later on, as I change D, the definition of training error changes, and it's important for you to realize this. Again, I'm not going to stop on all of this, but I want to point out to one other thing. Look at this expression here. What is this expression? Let's read it together. Sum over all i's such that y is different than h, which means all examples on which I made a mistake, dt of I times e to the alpha t. No, I'm just reading this expression. Altogether, it's equal to zt, but I don't care about it. I just want you to understand this expression here. You see which expression I mean? What is this? What is this expression? Now notice, e to the alpha t doesn't depend on the I. The sum is over I. So I can actually take the e to the alpha t outside the sum. So the sum is really sum over all I on which yi is different than ht, dt of I. What is this? It's the sum of the weights of the distribution over which examples? On those unmade mistakes. So what is this really? This expression is just epsilon. This is the error. The sum over all the examples, the sum of the weights of all the examples on which I made a mistake, this is just epsilon. So why do I say this? It's important for you to understand how to write down epsilon. What is the real meaning of epsilon? Epsilon is just the sum of the weights of all the examples on which I made mistakes. What is the second part here? It's same thing, sum over all I on which yi is equal to h, dt of I. Again, this e could go in front of the sum. So what is this guy? This is the sum of all the weights of the examples that I got right. All right? So this is 1 minus epsilon. Okay? So these are things that are steps in the proof. I don't care about the proof so much, but it's essential that you will understand what is epsilon, what is error, what is the meaning of error. Everything is written here and it's pointed out, so you can go over it and believe it. And the key question here is on the left. Why does it work? So the reason AdaBoost works is really the weak learning assumption. Because in every round, we know that we have something that is doing better than a chance. And as I said, this is a strong assumption. Nevertheless, it works very well in practice. Okay, questions on AdaBoost? Okay. So there's a lot more slides here that I'm not going to get into. I just want to point one thing. What have we done with AdaBoost? We boosted epsilon, the error. Remember that we started with this PEC learning definition that said, PEC learning says that you can get with high confidence, 1 minus delta, a hypothesis that minimizes the error epsilon for all epsilon. We assume that we have a box, a learning box, a weak learner that can do it, but not for all epsilon, just for epsilon that are better than chance. And we show that we can boost the epsilon to be as small as we want. Now, delta is actually easy to boost. I'm not going to talk about it, but that's basically by repeating the algorithm, you can boost delta. So the next two slides talk about it. You don't really need to know it if you don't care. The important thing is the boosting algorithm. Okay, so what is boosting? One perspective of boosting is as an ensemble method. You take a lot of learners and then you put them together. There are other methods that are ensemble methods. Bagging and random forest are such. They don't have the nice guarantees that boosting has, but they're very useful in practice. So I want to go over quickly and explain all of those sort of on common grounds. So what is boosting? We talked about we initialize all the training examples equally. We train a model on this weighted training set. We compute the error. We change the distribution in a clever way, increasing the weights on those that we got right, on those that we got wrong, decreasing the weights on those that we got right. We do it many times, typically hundreds or thousands of iterations, and then we return a final model, which is the weighted sum. That's boosting. Now, boosting, as I said last time, has been studied to death. There's a lot of theoretical interpretation of boostings. There's a lot of statistical interpretation of boostings. I'm not going to go into it. The important thing is that it has good theoretical guarantees, and magically it also works well in practice. Bagging is another way, again, to put together a lot of simple classifiers into one powerful classifier. In this case, we are generating multiple versions of predictors using something that is called bootstrapping. Yes?
What we did with the stumps with SGD, is that bagging?
It's very related to bagging, yeah. But let me finish the slides and we'll see. So how does it work? Just like in boosting, we have to think first about how do we generate the different versions. In boosting, we generated the different versions by different weights, different distributions over the examples, and then minimizing the error forces us to choose the different classifiers. Here, what we are doing is we are basically sampling the data set with repetitions many times. Every sample, we learn a classifier, and we keep on going. So every time we have a new training set, and then we just average the results. So again, this works. The key issue here is what you have is an unstable classifier. That is, when you work on some of the data set, you get a classifier. When you go to work on another subset, sample from the data set, you'll get a somewhat different classifier that will give you different results if you have a holdout test set. But overall, if you do it a lot, you'll get a more robust classifier and a good classifier. So what did we do in the homework? How did we get the different classifiers?
We did all the stumps, so we grew trees, and then we used those as features.
But why did you get different trees? Why didn't you get all the time the same tree? Exactly. So it's just like what I say here. Every time you have a different data set, you train, you get a different tree. Overall, we average them. Only that we didn't just average, we actually had supervision, so we could learn weights for the average, right? We use SGD. In bagging, in general, you don't have to do this. You can just, you're going to do it so many times, averaging is going to be sufficient. So this is an example of this. Draw 100 bootstrap samples of the data, which is kind of what we did. Train trees, you get 100 trees, and then average the prediction. That's bagging. Random forest, I call it here bag trees ++. Typically do a lot more than just bagging, but the idea is quite similar. You want to learn a lot of different classifiers, and in this case, you get different classifiers in two ways, or for two reasons. One of them is because you sample the data, just like in bagging. In addition, you also sample the features. You don't show in each round all the features to the classifier. You have 1,000 features, 20,000 features, you sample a subset of the features, and you train only using these features. Right? So essentially, you project your examples on a smaller instance space, and then you learn. So typically, when people use random forest, they use a lot more classifiers. So more than thousands, sometimes tens of thousands. But the basic idea is the same. You train a lot of classifiers, you then average them. These are considered very, very robust learning methods. Okay, questions? Okay, so I want to spend a little bit of time on multi-class classification. So far, everything we did really was binary classifications. And there's a lot of interesting stuff that goes on when we want to move from binary classifiers to more than binary classifiers. And in fact, there's a lot outside binary classifiers. There's just multi-class classifications where you have K labels, but you can think about multi-label classifications where you want to assign each example with a set of possible labels. You can think about ranking. You can think about hierarchies, classifying into, say, a tree, where the idea is that you want to label each example with a node in the tree, but if you have 2 nodes in the tree, maybe it's more important for you to be, you can make mistakes, but the type of mistakes that you want to make really depend on the tree. So it's okay if instead of getting this node, you get a node below it or above it in the tree, but you don't want to get a node in a different subtree. So for example, if you have topics, news articles, and rather than getting football, you're getting sport, that's okay. If rather than football, you're getting finance, not okay. So if you have a hierarchy of labels, maybe you want to think about how to train with penalties that are not symmetric. They really depend on the tree. Some mistakes are going to cost you more than others. So there's a lot of stuff going on outside binary classification. We're not going to talk about it. We're just going to talk a little bit about multi-class classification. So this is going to be our setting. Given a data set with multiple labels, K labels, I want to be able to learn a function that output a single label out of this. Suggestion, so how do I do it? In the rest of the discussion, I'm going to assume that we already know how to do binary classification. If you want, you have a box that does binary classification. And we want to use this box in the context of multiple labels. How would you do it? Yeah?
Multiple outputs, and then do a sigmoid of the outputs and choose which are highest.
Okay, so how do I train? That's the right way to make predictions. But first of all, how do I train my model?
So for binary, you have yes or no, or like 1 to -1.
Yes.
The other one you have, let's say, you have 10 classes or 5 classes, you have 0 to 4.
Yes.
So you labels are going to be 5 different classes, and you train with the same training. So output is going to be 5 different possible options, whichever is going to be the right answer. So I guess it depends on what algorithm you use.
It doesn't matter which algorithm. I have a box that is a binary model. Let's say SVM, okay? And let's take your example. I have 5 labels, 1 through 5. What will be the output of my training at the end?
SVM.
Yeah. No, just a second. Binary classifier. What is the output of the SVM? No, it's not a label. What's the output of the SVM algorithm? Someone there said the right thing that I'm expecting to hear. a weight vector, all right? The output of SVM is a W. Now, how do I use the W? Give me a new example. I'm going to do the dot product and threshold it. If it's positive, I'm going to say yes. If it's negative, I'm going to say yes. So the output of my box, let's say the SVM box, is a weight vector. What's going to be the output of your box with 5 labels?
Will be 4 weight vectors.
Why 4?
So we used 1 to say if it's 1 or 0. That's because it has 2 directions.
Okay, so one suggestion is 4. But if you have 4, how would you use it? What's your suggestion? 4?
Actually, it's
5. You want 5. Okay, so you'll have 5 weight vectors. How would you train weight vector number 1? What's the semantics of weight vector number 1?
It's either class 0 or class 1.
Okay, let's call them 1 to 5. So weight vector number 1 is class 1 or?
Class 0.
I don't have class 0.
Oh, let's say class 2, yeah. From 1 to 5, so class 1 or class 2.
Okay, so what does it do if I give it an example of with label 3?
Class 1 or other classes.
Oh, okay. So the suggestion here, so now we have a suggestion. So let's summarize. So we have 5 weight vectors. Weight vector number 1 is good at distinguishing labeled 1 from all the rest. So how do I train it?
I do it as a binary, say either that or the other one.
Right, so basically I take the examples that have 5 labels, 1, 2, 3, 4, 5. Those that are labeled 1, I call them positive for the first weight vector, and all the others I call them negative. And I train my box, and I got a weight vector. Now I'm going to take examples that are labeled 2, and I'm going to call them positive. All the rest I'm going to call negative, and I'm going to get another weight vector, the second one. And I'm going to do this 5 times. Everyone buys this? That gave me, as a function of my binary box that I learned a few weeks ago how to do, now I have a 5-way box. And this algorithm is called 1 versus all. So it's an example of what I call here a scheme for multi-class classification, that I reduce the problem of multi-class classification into a binary classification. Now, I suggest here 4 methods. We're going to only do 2 of them, because we don't have time. There are slides for everything, so if people are interested, look at it. You don't need to know it. It's not going to be in the exam. Only those that have V's on them will be on the exam. Yes?
Why is it not enough to have 4 weight vectors? Because like if all of them give you 0, then it would be else than the 5th time.
How would you train the 4?
It would still like say which one was labeled 1, 2, 3, 4, and then anything that was not labeled any of them would be.
No. So let's do it in details. I want to train my first weight vector. Tell me what are the positive examples for it and what are the negative. So this discussion is very important for all of you because it allows us to think about how to model problems. So please stay with us. So weight vector number 1, how do I train it?
I guess similar to like the homework we're doing now, like wouldn't you have, if you have 5 labels or 10 labels, when you're training it, you would have probabilities for each one? You would choose that.
No, but when I say training, I mean you have each example in the training data comes with a label, 1, 2, 3, 4, 5. You have a box that is binary. So you have to tell me, I don't know what to do with the 1, 2, 3, 4, 5. So you have to tell me, how do I change them to plus and minus? That's what my box knows how to deal with, okay? So tell me now how you're training your weight vector number 1.
You find.
You had to change the data first, right? So what is going to be the plus here?
All the ones that have label 1 in the training data.
Okay, all those that are 1 are pluses, all the rest are minuses.
Yeah.
Okay, got one weight vector. Let's move to the second one.
I do the same thing. I look at, like, in my training data, which ones are labeled 2, and I put that plus, and the rest are minus.
Yes.
And I go
3 and 4, okay.
It's like everything that wasn't in these 4 categories must be in the set.
Okay, I can do this. What's the downside of doing it? Yes?
That kind of assumes that they're perfect and only one of them claim at a time. But if 2 of them claim at a time, then you might have to look and say which one's more confident. And if you're missing that 5th classifier, you won't know how confident that 5th classifier is. So you won't know whether the 5th classifier would have also fill out that example.
Yeah, exactly. Everyone is with us? You could hear it? So the issue is that if you're perfect, yes, 4 will do. The rest is the rest. But because it's not, really what I'm going to do is I'm going to do a competition between the 5. And for every example in my test, I'm going to ask, who claims this more?
So is that like saying, like in the context of random forest, like when you can look at whether for training or for prediction, you can look at what the prediction is, but you can also look at the number of votes, and then look at. And
I actually do that. Random forest is doing averaging, which essentially is rephrasing what we just said. How many of them want this example, right?
So what's the classification and how confident your algorithm was?
Yes, yes. This is exactly what it does. So that's what 1 versus all is going to do. So let's do this in a more concrete way. This is basically what you just said. The assumption is that each class can be separated from all the rest. And therefore, when I learn, I decompose into k independent binary examples. So if D is the set of training example, for label L, I construct a binary classifier that says positive example are those that are labeled L, negative examples are those that are not labeled L. I learn k binary classifiers. K is the 5 that we had. And then I do winner take all. So I'm taking my new example X, I'm computing w.product X, and I do argmax. Who wants this example more, basically? Okay, so this is pictorially what's going to happen. 3 class labels, green, blue, black, and I'm going to learn, I'm decomposing it into binary classifiers. So first of all, I learn one that separates black and the others. Then I learn blue versus the others. Then I learn green versus the others. Everything is simple. Okay? Now, the problem is, what if I also have this red? What's the problem that this red introduce? Say it again. They're in the middle, which means what kind of problems do they cause me? I cannot use this linear separate. I'm assuming that my base classifier is linear now. But if it's not linear, whatever expressivity that you'll give me, the same picture is going to hold. So the problem that this red cause me is that I cannot linearly separate them from all the other colors. So this assumption that one color is separable from all the others held here doesn't hold anymore. So it complicates my life a little bit. I don't know what to do here. Which shows us that 1 versus all, even though it's by far the most commonly used scheme for multi-class classification, doesn't have theoretical justification because it makes a strong assumption that sometimes holds, but doesn't necessarily have to hold. Really, the problem is, this is how we learn, right? We learn 4 labels in this case, but for the red, it's not going to hold. I like to think about it as this example, as this Voronoi diagram. We cannot solve this Voronoi diagram problem with 1 versus all. So what are we going to do? We're going to move to a second scheme of multi-class classification, suggestions. How can we improve over this one versus all? Nevertheless, remember that this is the most commonly used scheme. People use it. It's not perfect. So if I want to improve, what will I do? Yeah?
I guess it could be something like binary search, where you have one classifier that says, well, it's either in the red-black class or the blue-green class, and then you have another classifier that says, well, if it is in the red-black class, then it's red.
Okay, but I want first to think about the training. All right, so how do I train? So when I say training, again, I'm assuming that I have one box which is binary. So what I want you to tell me is, here is the data. The data is 4 labels, black, blue, green, red. Tell me how to train my binary classifier. Okay, now continue.
So for the first classifier, you make all your red or black positive and all your blue or green negative. Then for the second classifier, the one that distinguishes between red and black, you feed it only the red and black. You forget about all the blue and green. And you make all the red positive and the black negative.
Right.
And for the other classifier that distinguishes between blue and green, you forget about all the red and black.
Okay, so let's summarize what Daniel said here. So before I had K labels, how many weight vectors did I have? K. Now I have K labels. How many weight vectors do you want me to have? K choose 2. Every pair. So I'm going to have one that separates between black and green, one that separates between blacks and blue, blue and green, green and red, and so all pairs. So basically, what I'm going to do is positive examples are going to be all examples with label I, negative examples, all examples with label J, all those that are not I and J, I'm going to throw out the window for now, and I'm going to learn an IJ classifier. And I'm going to do this for all pairs IJ, so I'll have K choose 2 classifiers. So basically, this is how it's going to look. I'm going to have this, I'm calling the weight vectors V now, other than W. I'm going to have a VRB, which says yes if it's red, no if it's blue. I'm going to have VRG that says yes if it's red, no if it's green, and so on, for all pairs. And this will allow me to solve this Verona diagram, but what kind of complications do I get to? How do I evaluate at the end?
You need weights. I don't know how the question. How do you, like, yeah, at the end to make one classifier, how do you put it together?
So how do I put it together at test time? Yes?
I think this is actually a little bit different from what I was saying, because this is for every pair.
For every pair.
I was only saying each classifier basically splits it in half. So I think my idea was you have log K classifiers.
Okay, you can do that too. This is a simpler mechanism. We're going to say something about yours. Here it's clear how to train, right? I basically look at my data, I split it to all pairs, and I train. The problem is how to classify, how to put it together into one model, and there are multiple ways of doing it. One of them could be majority. So give me an example. I'm going to run it through all the examples, and I'm going to count how many classifiers think this is red. And I'm going to do it this way. Another could be to do a tournament. Basically, I'm going to first ask all the n-square classifiers. Red versus green. Let's start from here. So red versus, what is it? Blue. And then blue versus black. And black versus green versus blue, and so on. And every time I'm going to surface a winner. And then ask the pairs that remain. And I'm going to keep on going this way until I have a winner. In all these cases, weird stuff can happen. Why is it that weird stuff can happen? Think about it. Here is an example. Let's say it's red. Now, my black versus blue classifier in training has never seen a red example. it was only trained on green versus blue. Now I'm asking it to predict on a red example because I don't know which example it is, so I'm giving it all the examples. It can do weird things. So the evaluation in this case is not necessarily stable, but again, it's another relatively robust method. I want to compare for a second between these two methods, just in terms of accounting. And this will also allow us to make sure that we understand how these work. Let's assume that I have M examples. I have K class labels. So for simplicity, I'm going to assume that everything is uniform. So I have M over K of each class label. Okay? So let's do the accounting and see what happens in one versus all versus what happens in all versus all. It's called all versus all. Sometimes it's called all pairs. So in the one versus all, I'm going to have K classifiers. The ith classifier is going to take M over K positive example, and M minus M over K negative examples. Everyone agrees? Again, M over K positive, and the rest negative. That's what it says here in the first row. And then so it's easy, right? So I'm going to do this K times for each of the Ks, and I have K classifiers. And then the decision is basically winner take all, argmax. In all versus all, what I'm going to do is I'm not going to use all the data for each classifier. What I'm going to do is I'm going to take M over K i's and M over K j's and send them to my box to learn the ij classifier. So I'm only using 2 times M over K of the data. The rest I'm throwing out. And I'm doing this K choose 2 times. At the end, I have K square or K choose 2 classifiers, and I'm running my decision thing, which I say sometimes is unstable. Okay, so which one is better? Any views, any suggestions, any thoughts? Yeah?
I think one versus all. I don't know. It just seems more.
Okay, so as I said, one versus all is the most popular method, only that we've seen that it's not expressive enough, right? So the Verona diagram example with the red in the middle, this is just one example, of course, it's not expressive enough to deal with it. Now, the truth is that in very high dimensional spaces, these cases never happen. In very high dimensional spaces, everything is linearly separable, so this will not happen. In medium dimensionality, this can actually happen, and then one versus all is not going to be expressive enough. All pairs or all versus all is going to be expressive enough. Yes?
Wouldn't it also depend on your data set? So for example, because if you have if a data set is small, like in the number of rows, and you take it to very high dimensions, then wouldn't that be a bit of an issue? So basically, if you have like a lot of rows, wouldn't all versus all work well?
Okay,
one of the cons there is like you have less examples to learn from, right? But if you have enough examples, then that should be.
Okay, so let's assume that in terms of expressivity, I'm okay here, right? So I can learn one versus all, I can learn all versus all. Which setting is going to be more efficient? First one, why?
Because you don't have to do K squared linear classifiers.
Okay.
First you have less weights, and then at the end, when you're trying to evaluate, you don't have to do argmax.
So one suggestion is the first one is more efficient because you learn only K classifiers. Anyone wants to disagree with that? Yeah.
You also have to train on more examples for classifier in the first one, because in the first one you're training on m over k plus k minus 1 and then in the second one you're
Yeah, so if I sum up the positive and the negative, you're exactly right. So in the first one, I'm training on m examples. In the second one, I'm training on m over k times 2. Let's say that k is 100, m over 50 every time. So I'm training more classifiers, but each one of them on a lot less data. So it's not completely clear which one is going to be more efficient. In fact, to really think about it, think about dual primal, bringing back all the idea from 2 weeks ago, but it's a good thing to think about. So think about when you train SVM or perceptron in the primal way, learning the weight vector, what is the complexity? It's a function of the dimensionality, really linear in the number of examples. If you train in the dual, it costs you more in terms of the number of examples, remember? Because every time I have to remember all the previous examples, and when I predict on this example during my training, I have to touch all the previous examples. It's quadratic in the number of examples. So if you go back to the slides when we talked about complexity of running perceptron versus dual perceptron, you will see that when you run in the dual, you want to have less examples. Okay? We actually had a slide that talked about that. Now take this slide and implement it here, and you will see that when you run in the dual, actually all versus all is better. It's more efficient. Because you learn more classifiers, but each one of them is more efficient. In fact, if you go to the best SVM packages, the best package is libSVM from National Taiwan University. You'll see that they figured it out, and they train multi-class classification in all versus all, not in one versus all, exactly for this reason. So it took some time for people to realize this, but this is how they do it because it's more efficient. Question?
Just bring us a question. Does the choice of this have anything to do with the ratio of like rows and columns, or not at all? Like how many examples and how many features you have, or not?
So I'm assuming that it has everything to do with the number of examples. As I said, if I have a lot of examples, dual is going to suffer more. And therefore, I want to use all versus all because it's more, it uses less examples. It does not use all the examples every time. Yeah, so it definitely has to do with the number of examples. I'm fixing the number of features here because it's basically the same for all methods. Okay, so we covered two important things. We talked a little bit about the fact that there is an issue of we are decomposing the multi-class classification into binary classification, and we have to think about the fact that sometimes it's going to suffer. I skipped an algorithm that I called here error correcting codes, which is somewhere between, if you want, all versus all and one versus all. It's an interesting algorithm. The slides are here. I just hid them. It's a little bit related to the ideas that you suggested. You can look at it. I want to jump directly to give a hint on another approach. How do I really train, for example, SVMs? So in order to think about it, I'm putting these graphics here, which is really what happens when we do one versus all. This is a picture of one versus all. So each one of the suns at the top here represents a label. And I'm learning each label as a function of all my features independently of the rest, right? So when I learn the first weight vector, going back 20 minutes ago to the 5 weight vectors that we learned, when I'm learning one weight vector, I don't know about the existence of the others and how well they're doing, right? I'm just taking positive examples that are labeled 1 versus the rest. When I take This second label, I'm training its positive example versus the rest. So that's the picture. That's one versus all. Now there's another way of doing it. Again, let's think about the binary case. I can think about the binary case as one label. Yes, if it's positive, no, if it's negative. But I can also think about binary as having two labels, the 1 and the 2. And I'm going to train them independently. Right? So what does this give me? This gives me a little bit more expressivity. Essentially, I'm training, I have two weight vectors for a binary classifier, and you can see it here. So a weight vector that I call the W plus, connecting these features to this positive node, and a weight vector that I call W minus that connects the negative label to all the features. How do I update? I could update in the usual way, and then W plus is going to be just the same or the negative sign of W minus, but I could also update it in a more sophisticated way, which I'm suggesting here. Basically, I'm going to say that the effective weight is the difference between W plus and W minus, and I'm going to update them together. So every time I'm going to change W plus and also change W minus. In this case, the way I've written it in the context of we know, where I multiply W minus by something and multiplying W plus by something. But you can do the same thing for perceptron, you can do the same thing for any other algorithm. What is the advantage of this algorithm? The advantage is that it ties together the two weight vectors. And when we do multi-class classification, when I'm generalizing this from 2 to 5 or to 17, this is going to solve this Voronoi diagram problem directly. I'm not going to show why, but by the way, this is the question that you asked me last time about why do I do softmax, and it helps. That's what you're doing here. You're basically tying multiple weight vectors together. Again, in the slides, I'm explaining this in more details, generalizing this picture to more than 2. I'm not going to show why it solves this Voronoi diagram problem. Instead, I'm just going to talk about the context of multi-class SVM, which really implements this idea indirectly. So let's remind ourselves in the next minute, what is SVM doing? SVM is trying to maximize the margin between positive example and negative example. What do I do in multi-class classification? I also want to maximize the margin. What is the margin? It turns out that the right way to think about the margin is to think about the labels and look at and define the multi-class margin as the gap between the top scoring and the second scoring function. That's the margin. And now you can write the same SVM objective function that we did last time, and you can do it this way, with maximizing this margin. It's going to look like this. So we have the same objective. This is the sum of W squared, but I'm going to do it instead of one W. I have now sum over all Ks, the K Ws that I have, the same K that we had at the beginning, 1 to 5. Subject to, this is how I'm writing the constraints. Instead of just making sure that each W, just in the standard binary case, W dot product X is greater than 1, here I'm looking at the difference between Wix and Wkx for all Ks, and I want this to be greater than 1. So this will be the equivalent for maximizing the margin between I, which is the correct label, and all the other Ks, all the other candidate labels. So this is how multi-class SVM is going to work. There is a little bit more of explanation here. I'm going to skip it. Before I'm done, I want to say two other things. So what I'm going to start next week is talking about probabilities. And maybe I'm going to wrap this up and talk about probabilities. I want to ask you to refresh your memory with what is probability, because I'm going to not spend a lot of time there. If you go to the slides that are out already of this lecture, okay, that doesn't matter now. You will see about 20 slides that remind you of key concepts in probabilities. I think that you all know it. If you don't know it, this will be a good chance between now and Wednesday to go over these slides, refresh your memory of the terminology. It's in the slides, but I'm not going to cover it. I'm going to assume that you guys know this, and I'm going to start talking about generative models and probabilistic learning. Okay, if you're not going to be here on Wednesday, have a good Thanksgiving. Otherwise, see you on Thursday, on Wednesday.
Doing the multi-class classification anyway.
They are doing one versus all.
Okay, yeah, but still it is doing it. So.
Well, it depends. It depends. If you have a binary classifier, they're just doing binary, right?
I mean, it depends on the input you give, like either.
No, it depends on the labels, right? So it depends on the data, right? So if the data is binary, it's just doing binary.
Okay.
If the data is multi-class, it's doing one versus all.
Oh.
Right?
So, yeah, it's
but,
probably related.
Yeah.
Your network is really doing this in multi-class.
But it depends on the label, as I said, right? So if you have multiple labels, yes, yeah. But again, it's doing the standard training is just doing one versus all, which hopefully now we understand is not necessarily the right way. It has some limitations. Yeah.
I'm not sure if it matters, but like, technically, the stuff we did with the stump, is that an ensemble method? Yeah. It is, right?
Yeah.
What exactly?
It's just combining classifiers, right? So combining classifiers, right?
Say it again?
What exactly the meaning of ensemble?
Ensemble just means that you learn a lot of simple classifiers and you put them together.
They don't have to be weak classifiers by that definition. They just have to any, right? Doesn't matter. Strong, weak, medium.
Yeah. Even in boosting, the idea is you don't have to learn weak classifiers. It just allows you to not work too hard on each classifier. But if you do it, if you have better classifiers, you see from the bound, the gammas are going to give you the bound. If you have better gammas, larger gammas in this case, better.
Yeah, right? You get more fair, yeah.
It just says that you can
start with
you can suffer with even small gammas, but if the gamma is large, better.
It's a comment that the classmate make correctly in the sense like, say I find the best classifier, and the best classifier is error 70%. If I just change my prediction to the opposite one, then I could get accuracy 70% instead of error 70%. So that can you always do that? But in that case, then you can always get the classifier you want, unless you get 50%, and even then, probably wouldn't matter. Right? If my accuracy is like 0.14, then I just reverse whatever I think is correct. I just reverse it, and then I get accuracy of 6.
Yeah. You can always do this. But how do you actually do this in practice?
With the training, you can just, I mean, I really hoping that in the general as well. But in the training, I can see, like, okay, I have a rule that predicts all my instances, and I am only correct 14% of the time. So then I say, okay, I'm just going to reverse all my predictions. But then, with that generalized well, like, is that the same as literally training a weight vector that gives me directly the 86%?
No, so the idea is that what you have is a learning algorithm, right? So your learning algorithm does something. It's a black box. You don't do evaluation. You run your learning algorithm. You output something.
Yeah.
And this is what you put into your model, right? You don't say either give me the output of the learning algorithm or give me 1 minus the learning algorithm.
No, but in the case of a tree, say, I can have all the nodes and say, this node is positive, this node is negative, blah, blah. I can just reverse, say, like, all the nodes should have reversed.
When are you going to do this?
At the end. Once I know
At the end of what?
At the end of my training, when I know that my training error is super high, it's like 84% error.
Then are we even really training?
But then you're not really training your learning algorithm here, right? Because what have you done really? I mean,
Yeah, exactly.
so what you need is a model. Right? What you're saying is I have a model, and I don't believe this model, I'm changing the definition.
Like the opposite of it.
Yeah.
But
You
then you're
learn
not
nothing,
training
right?
actually,
You learn nothing.
So then what he said doesn't stand, right? Because that's what he's saying, right? But there is
I
something
get
in
the same
model.
answer, right? So,
I thought I didn't understand the answer, that's not here.
so basically, what you care about is not the prediction. What you care about is the model. Right?
Also, then that doesn't, then you cannot do it, right? You cannot just reverse the science and then you think, oh, I'm happy. It's like,
No, because next time we give you new training data, what will happen now?
in theory, I would put it through my original model and then reverse at the end and say, whatever my model said, I'm going to do
So if
that.
that's your model, that's fine. But then always do this.
Yeah. That's what I'm, can you do that?
If you do it always,
Yeah.
then it's
And
a
in
model.
theory, would that generalize the same as if my original model really gave me a high accuracy?
So all you said is my model is the function 1 minus w dot product x.
Yeah.
That's a good model.
Okay.
But don't tell me,
But isn't the
you know what,
implication
first
that
of all I'm
can
going to
always
look at the data and then I decide whether I do w dot x or 1 minus.
Oh, I cannot
That's
do
not
that.
a good algorithm.
Oh, I thought
That's not going to hold.
I cannot do that, like, train the model in the training. Once I know what's the error, then decide how I'm going to use it in
Okay,
the
so
prediction.
let's think about what does that mean? What does that mean? What have you learned here? Now I give you test
I
data.
learned I'm really wrong.
No, I give you test data. Right?
That's what I learned, like, I'm
No,
really
but
wrong.
I give you test data. So which of the two are you going to use for prediction?
No, so my point is, like, let's say I only take my training data. I run my algorithm, I get a rule, I had an output, and I realize my error is super high, 90% error.
Okay.
Now I say, oh, in the future, when I apply this to unseen to the test data, I want to reverse the rule.
That's fine. You can do
That I
that.
can do it.
So that's your model. But fix it now. Don't tell me,
After the test
sometimes
data,
I'm
yeah.
going to
No.
decide.
But it's okay to fix it after the training, before the testing.
Yes.
Okay, got it.
That's a model. It's just a different function. Right?
Okay.
But you cannot just say,
But then if you do that, can't you always do well, quote unquote well? Because if you do really shitty, say I have like 10% accuracy, then I do my model negative of my thing, and then I get like in theory. But then what is my generalization about? Like how do I know that it will turn? You see my point? Like if I learn that I'm really, really wrong, and I'm just saying doing the opposite might mean that I'm really, really right.
So do the following thing. So split your training data to 2.
Yeah.
Run your model on half the data.
Yeah. Let's say I'm super wrong. 90% wrong.
Yeah. Now run it on the second half of the data.
With the flip sign, for
Yeah.
example.
What-
And then
what's
if it
gonna
does well,
happen now?
in theory, it should do really well.
So now you have a model that does very well on all the data.
Okay.
It's a good model.
Is that used? Is that often used? Where
No.
you just reverse?
No, because the model should have learned directly the stuff that learns better on the data.
But you say theoretically it's okay.
Yeah, it will not happen, right? All I'm trying is basically kind of it's a thought
Because what if I'm a,
Experiment.
yeah, but like if I'm a PhD student, I build this super complex model, crazy model, and it's like super shitty accuracy, and I say, well, my function is the negative of this, the opposite of this model, and then I say I can
The
graduate.
issue is that
Can
if your
will you
model,
let me
if your
pass?
model, if your model did very shitty, it's going to do very shitty.
But I know it, now it does well, because I just said like I'll do the opposite of what my model learned, right? I'll reverse it, like what I said.
Then it's a good model.
Okay. But then my point is like no matter what I train, I just like I'll train some model and then I decide if it's that or the opposite of that rule, and then I'm like happy person. And it's just almost the same thing. And if it does very well, very poorly, I just try to find something that's not mediocre, and then I just reverse it.
So I was wondering if, would it be possible for Samuel to be in like the first 10 or so, just because I would like.
Yeah, sure. You can just go search for the end.
Video, so I last week I did a new video,
Okay.
which I've also included mine, but so can you play out the video to me now?
When do you submit it?
12.
Okay. Let me.
Because there was some issues with like uploading it on video to the blog.
Let me just make sure I have your most recent.
Thanks.
So fixing this